Part C of the question asks you to prove or disprove this claim. If you are given that f of n is big O of g of n, does that imply that the log of f of n is also big O of the log of g of n? There are some additional conditions given here whose purpose will be clear as we try to work out this problem. For now, you can just leave them aside as conditions that are necessary for certain things to work out in the solution. So let's start with what has been given to us. We are given that f of n is big O of g of n. What that means is there exists a constant c greater than 0 such that for all n larger than some threshold n naught, f of n is bounded from above by that constant multiple of g of n. This follows from the definition of big O. This is the definition of big O. And we need to prove that, either prove or disprove, that there exists a constant k greater than 0 such that for all n greater than some threshold nk, log of f of n is less than or equal to or is bounded from above by some constant multiple of the log of g of n. This again is the definition of big O. So if you are given this, can we prove or disprove the box on the right hand side? So let's see. If this is our starting point and this is where we need to end, how do we attempt to transition from here to here? If you notice on the right hand side, instead of f of n and g of n, their logs are present. So why don't we try to take the log of what is given to us? So let's take the log of both sides. If a is given to be less than or equal to b, the log of a must also be less than or equal to the log of b. And that's because the logarithmic function is an increasing function. So if the argument to the function, if there are two arguments to the function a and b such that a lies to the left of b or a is less than b, then the logarithm of a will also be less than the logarithm of b. So this is the log of a, this is the log of b. So if x is always increasing, if log of x is an increasing function of x, then this will be true. Which is why when we take the log of both sides, we can claim that there exists a c greater than 0 such that for all n greater than or equal to n naught, log of f of n is going to be less than or equal to log of c times g of n. Log of a times b is log of a plus log of b. So log of c times g of n is going to be log of c plus the log of g of n. Now from this, is it possible to claim that log of f of n is less than or equal to k times log of g of n? Well, we know that log of f of n is less than or equal to log c plus log of g of n. Now, if we are able to somehow show that this in turn is less than or equal to this, then by transitivity, log of n would be less than or equal to k times log of g of n. So we need to prove let me go to a new page here. We need to prove that f of n, which is given to be less than or equal to, log of f of n, which is given to be less than or equal to log of c plus log of g of n, is less than or equal to this right hand side, log of c plus log of g of n, is less than or equal to k times log of g of n. For some k greater than 0 and for all n larger than some threshold n sub k. Okay, so this is given. This is given to us, and this is what we need to prove. And if you're able to prove this, then by transitivity, we have proven what was originally claimed in the problem, or the original claim that we need to either prove or disprove. So let's see. Here we notice that log of g of n is multiplied by a number here, whereas here it's just the coefficient of log of g of n is just 1, and you're adding a constant value to it. So intuitively, it may seem as though if you take log of g of n and you're adding a constant value to it, and on the other side, if you're multiplying log of g of n by some constant, it should be possible for this constant k to be large enough that the right hand side will be greater than or equal to this left hand side. But of course, we need to show that there does exist some constant like that. So let's try putting values for k. So let's say k is equal to 1. If k is equal to 1, then we get log c plus log of g of n is less than or equal to log of g of n. Now that's not true. If c is greater than 0, and especially if c is greater than 1, log of c will be positive. And if log of c is positive, then log of c cannot be less than or equal to 0. If k is equal to 1, then log of g of n will cancel on both sides, and we'll end up with log of c less than or equal to 0, which is not necessarily true. Especially if c lies between 0 and 1, that won't be true. If c is greater than 1, this won't be true, because log of c then will be positive, whereas the right hand side will have just 0. So note in particular that c can be any constant that is positive. It could be between 0 and 1. It could also be larger than 1. And without loss of generality, let's assume that c is actually greater than 1. Why? Because let's say c was, let's say that this constant for which this condition holds, let's say this c was between 0 and 1. Now if this inequality applies for a number between 0 and 1, it would definitely apply for a number that is greater than 1, because by replacing this number by something larger than 1, we're actually increasing the right hand side further. Right? So if we take c on the number line here, if this inequality holds for this value of the constant, then it's going to hold for this value, it's going to hold for this value, it's going to hold for this value, because as we are increasing the value of the constant, the right hand side is increasing more and more. So let's assume that this c is greater than 1, so log of c is positive. So if you put k equal to 1, we are not going to get, this inequality is not going to hold. What about k equal to 2? If we put k equal to 2, we get log c plus log of g of n is twice log of g of n. So if we take log of g of n on that side, we get log of g of n must be greater than or equal to log of c. Now, maybe that would hold for, well, it's not clear that this would be true. In particular, if g of n is, um, so what are we given about g of n? We're given that log of g of n is greater than or equal to 1. This would mean that g of n would be greater than or equal to 2 to the power 1 or 2, because remember that we are taking log base 2. But if g of n is greater than or equal to 2, it doesn't necessarily imply that log of g of n at some point must be greater than or equal to c. That may or may not hold, because if log of g of n goes on increasing till infinity, if it's a purely increasing function of n, then we can say that at some point log of g of n is going to be greater than or equal to any constant you take, whether log c or a million or a billion or whatever value of log c you want to take. So what about 3 times log of g of n? Well, I'm sorry, this is actually not log of c. This is actually, yeah, it is log of c, sorry. So let's try to choose a value such that not only will g of n cancel on both sides, but maybe log c will cancel as well. So so let's say we put the value of k to be equal to log c plus 1. Why do we want to do that? Well, if we put k equal to log c plus 1, then one of the log gns will cancel with this log gn on this side. And then we'll be left with a single term saying, which will say log c times log gn. And on the left hand side we'll be left with only log c, because log gn would have cancelled with one of the log gns here. So by choosing this constant, we will ensure that even the log c's will cancel out. Right, so let's put k equal to log c plus 1. This will make log c plus log of g of n. Or rather, we need to prove that log c plus log of g of n is less than or equal to log c times log gn plus log gn, g of n. Now this will cancel with this, and this log c will cancel with this log c. So we'll be left with log of g of n is greater than or equal to 1. Okay, so this is log c equal to, less than or equal to log c times log of g of n. So this implies that log of g of n needs to be greater than or equal to 1. For this inequality to be valid, this condition needs to be satisfied. That's what we have shown so far. We are trying to ascertain if there exists some k and some threshold large enough beyond which this inequality holds. Because if this inequality does hold there, that means log of f of n is going to be less than or equal to k times log of g of n, and we would have proven the original claim. Now for this inequality to hold, we have shown that if we put k equal to log c plus 1, then we get this condition. This needs to hold. But this actually does hold, because we are given in the statement of the problem itself that log of g of n is greater than or equal to 1. This means, and the other thing we are given is f of n is greater than or equal to 1. And the reason that's given should be obvious, because if f of n is greater than or equal to 1, only then will log of f of n be positive, will be positive. Otherwise, it will be negative, and since we want to preferably have positive functions over here, that condition is given as well. So if log of g of n is given to be greater than or equal to 1, then we can put k equal to log c plus 1, and we can put n sub k equal to n naught, because in the original condition, the premise, or what we have been given at the beginning, is that log of f of n is less than or equal to log c plus log g times g of n for all n greater than or equal to n naught. So we don't have to change the value of that threshold here. For this, let's take the same threshold value and let's put k here as log c plus 1. And what we get is that k times log of g of n is going to be greater than or equal to log c plus log of g of n. And therefore, log of f of n is going to be less than or equal to that constant k, which is log c plus 1, times log of g of n for all n greater than or equal to n naught, or n sub k, which is equal to n naught. This means that log of f of n is indeed big O of log of g of n. So the original claim has been proven to be true. If f of n is big O of g of n, log of f of n is going to be big O of log of g of n. We can verify this by taking some examples. Let's say we take f of n as n square and g of n as, say, 2n square. So f of n is big O of g of n. What's log of f of n? Log of f of n is going to be 2n. Log of f of n is, log of f of n is going to be twice of log of n. And log of g of n is going to be log of 2 plus log of n square, which is twice log n. Log of 2 is 1. So is twice of log of n in big O of 1 plus twice log n? Okay, 1 plus twice of log n is in log n. So we can actually remove these constants and drop this lower order term, because the rate of growth of this expression is really log n. So is twice of log n in big O of log n? Well, yes, it is. So this is an example where this condition, which illustrates how this condition is actually true. We can take another example. Let's take f of n as n square and g of n as twice of n cube. Now log of f of n will be the same, twice of log of n. Log of g of n will be 2 plus 3 times log n. So is twice of log n in big O of 1 plus 3 log n? Well, 1 plus 3 log n again can be written as log n for the purpose of the big O notation, because it grows at the rate of log of n. And indeed twice of log n is in big O of log n. So again, this illustrates that the claim is true, and we have formally proven it also. To just take examples of functions and find that this implication holds is not really a formal proof, because it's possible that there could exist other examples for which this implication doesn't hold. So positive examples can be used at most to understand or to um, back up or to just indirectly support the actual proof. It cannot be used to, it's not a proof in itself. So a formal proof will go something like what we did over here. These examples are just illustrating that this condition does hold for the functions that we've chosen.